Welcome to lecture 7 on Essentials of Topology. In the previous lectures, we have recalled the concepts associated with sets, functions and metric spaces, which we have to use in the next lectures. Even we require some more concepts which we will recall as per their requirements. In this lecture, we will discuss the concept of topological spaces. The topics which we will discuss are topology, open sets, as well as some of the examples of topology. Begin with the concept of open sets in a metric space. We have seen in the last lecture that in a metric space, xt, empty set and x are open sets. Finite intersection of open sets is open and arbitrary union of open sets is open. In the next, what we are going to do is that we are going to forget the structure, that is D available with x. We will begin with a non-empty set. We will take collection of some subsets of x, and after that we will put some restrictions like these things, and we will get the idea of topology. So let us begin with the formal definition of topology. Let x be a non-empty set and tau be a subset of power set of x. Then we say that tau is a topology on x if empty set and x are members of tau. Tau is closed under finite intersection, that is, if g1, g2 up to gn are members of tau, then their intersection, that is g1 intersection g2 intersection up to gn, also belongs to tau, and tau is closed under arbitrary union, that is, if there is a family of subsets in tau indexed by a set I, then union of gi, I belongs to I, also belongs to tau. If tau is a topology on a set x, then this pair x tau, this is called a topological space. And one more thing, each g in tau is called a tau open set or simply an open set. Let us take some of the examples of topology. The first one, why not to take the topology associated with metric spaces, because what we have seen, the definition of topology itself is inspired from the concept of open sets in metric spaces. So let xt be a metric space and tau is a collection of some subsets of x such that for all x belongs to g, there exists r greater than 0 such that the open ball centered at x with radius r is a subset of g. If we are looking this definition, this can be rewritten as that this is g subset of x such that g is an open set in metric space xt. As we have seen that empty set and x are open sets in metric space xt, it means that empty set and x both are in tau. We also know that finite intersection of open sets in metric space xt is open. So from here we can conclude that if g1, g2, gn belong to tau, it means that g1 intersection g2 intersection gn also belong to tau. We also have seen that arbitrary union of open sets in xt is open. So from there we can conclude that if we are having a family of subsets indexed by set I, then union of gi I belongs to I is also in tau. Or we can say that tau is a topology on X. This tau is a topology on X, and we call this topology the metric topology. Let us discuss some more concepts on metric topology. What we have seen that if we are beginning with a metric space xt, we can put a topology on X, and this topology is called metric topology. We will use a fixed notation for it. We will denote a metric topology induced by this metric space xt by using tau d. Second one, we already know that every open ball is an open set. Therefore, we can conclude that the open ball centered at x with radius r always belongs to this tau, x belongs to x, and r greater than 0. We will discuss some more concept about metric topology, metric spaces, and topological spaces. Moving ahead, let us take another example which is free from metric. So let us take x as a 2-point set AB. We are defining two topologies on X. Tau 1 is empty set X and singleton set A, and tau 2 is empty set X and singleton set. It can be seen that tau 1 and tau 2 both are topologies on X, as empty set and X both are already member of tau 1 as well as tau 2. If we are finding out their finite intersection, that will be either empty set X or singleton set A in this case, or that will be empty set X or singleton set B in this case, and similarly for union. That's why tau 1 and tau 2 both are topology on X. Now, if these are topology, what we can say that here open sets with respect to this topology are empty set X and singleton set A. These are tau 1 open set, or we can say that open set with respect to topology tau 1. But note that the singleton set B, this is also a subset of X, but singleton set B is not member of tau 1, so we cannot say that or singleton set B is not tau 1 open. Similarly, in this topology, the open sets are empty set X and singleton set B. These are tau 2 open sets. But note that singleton set A itself is a subset of X, but the singleton set A is not member of tau 2, and therefore this is not tau 2 open. Moving ahead, let us take some more examples. Begin with a non-empty set X, and let us define tau here as collection of empty set and X. it can be seen that tau is a topology on X, as this is containing empty set as well as X. Finite intersection and arbitrary union are obviously members of tau. Therefore, this tau is a topology on X and it has a special name. This is called indiscrete topology, or this is trivial topology on X. Even we cannot think about the topology which is not containing empty set as well as X. So we can have one more conclusion, and the conclusion is that this indiscrete topology is the smallest topology. Moving ahead, again begin with a non-empty set X and define tau as although G such that G is subset of X. Precisely this tau is nothing but power set of X. Then tau is again a topology on X as empty set is subset of X. X itself is subset of itself. Therefore, empty set and X both are members of tau. If we are taking G1, G2, Gn in tau, it means that G1, G2 and Gn all will be subset of X and their intersection, this will also be a subset of X, and therefore G1 intersection G2 intersection Gn belongs to tau. Finally, if we are taking a family of members of tau indexed by set I, then note that this Gi will be a subset of X for all I belongs to I, and therefore their union of Gi I belongs to I is also a subset of X, or we can conclude that union of Gi I belongs to I, this belongs to tau. Therefore, the tau defined here, this is a topology on X, and this topology is known as discrete topology. We have already seen that this tau is a subset of power set of X. But what we have taken here, we have taken tau as a power set of X itself. So what we can conclude from here, can we say that tau is the largest topology? Tau is the largest topology on any set. Moving ahead, let us take one more example. Let us take a set X as ABC. Note that the number of elements in X are 3. If we are talking about number of elements in power set of X, that will be 2 power 3, that is 8. Question is, how many topologies, on X can be constructed? 2 topologies are natural, that is indiscrete topology or trivial topology, and second is discrete. It is to be noted that this is the smallest one and this is the largest one. So can we construct some more topologies in between these two? Answer is yes. For example, let us take one such topology as tau1, this is empty set X and singleton set A. One can check that this is a topology. Let us take this tau 2 as phi X event AB. This is also a topology on X. Let us take tau 3 empty set X A B and this 2-point set A. This is also a topology on X. So in this way we can construct a number of topologies on X, and number of such topologies on X is, that is 29. So here we have constructed only few. One can construct the remaining topologies on X. Here it is to be noted that if we are taking a collection something like empty set X, this 2-point set AB and this is BC, or we are taking in the collection tau something like empty set X A and B. Note that neither this is a topology on X nor this is a topology on X. Question is why? Here is AB is a member of this collection, AB is a member of tau and BC is a member of this tau, but we are finding out AB intersection BC, that is singleton set P, which is not in tau, therefore this is not a topology. Similarly here the singleton set A and singleton set B both are in tau, but if we are looking for their union, this union is a set AB which is not in tau, therefore this is also not a topology. Moving ahead, let us discuss some more concepts about metric spaces and topological spaces. We are beginning with some of the examples. Let us take X as set of integers, and let us take this metric, that is the discrete metric on Z. This is defined as 0 if X equals to Y and 1 if X is not equal to Y. If we are looking for an open ball here centered at an integer, that is X belongs to Z, and let us take R equals to half, then we have already seen that this is equal to collection of all Y belongs to Z such that dxy is less than half, or this is simply all Y belongs to Z so that dxy equals to 0 from the definition, and that will be singleton set X. Also, we have seen that open balls are always member of the topology. So, corresponding to this metric, if this tau d is the topology, then this singleton set X will always be member of this tau d for all X belongs to Z. We can conclude one thing from here, that this tau d is a discrete topology, and this is possible because if singleton sets are member of topology, their union will also be member of topology. So all 2-point set, 3-point sets, and continuing with that one, all subsets of X or all subset of Z will also be member of topology. Meaning is that if we are beginning with discrete metric on Z, the topology which we are getting on Z is a discrete topology. Let us take another example on the same set. X is again we are taking as set of integers, but metric which we are taking, that is dxy, this is absolute metric, that is x minus y, our usual metric. Now again if we are looking for what will be the open ball centered at X and radius half, this is collection of all integers such that dxy is less than half, or this is collection of all integers so that this modulus of x minus y is less than half, or this is all those integers y such that y belongs to x minus half to x plus half, and that is nothing but singleton set x itself. With the same justification what we have discussed in this example, the singleton set X will belongs to tau d, that is the topology induced by this metric. And if singleton set is in tau d, we can conclude that tau d is a discrete topology. From these two examples, we can conclude that distinct metrics may induce the same topology. One natural question is here, what we have seen corresponding to every metric on X, one can find a topology. But what about the converse, whether corresponding to every topological space there exists a metric? Answer is negative. Let us take an example. Example is the simple one. Let us take X as 2-point set AB with indiscrete topology on it. What we can justify that even indiscrete topology cannot be induced by any metric on X. If possible, let D be a metric on X inducing this tau, then what will happen? We can show some contradiction. How is it possible? Because we have assumed that D is a metric, let us take D AB equals to R, that is greater than 0. Now we are constructing an open ball centered at A with radius R by 2. This will be equals to y belongs to x such that DAY is less than R by 2. But note that here is only two elements A and B with distance R. So that is precisely all y belongs to x such that DAY equals to 0, or that will be nothing but singleton set A. But as we already know that every open ball is an open set and that will always be member of topology. But note that singleton set A is not member of this tau, and therefore no such metric is possible. So what we can conclude about metric spaces and topological spaces? Answer is here, and the answer is given by this diagram. Let us take the first one as a collection of metric spaces, and second one is the collection of topological spaces. One thing is clear, that corresponding to every metric there exists a topology, that we call metric topology. Also corresponding to two metric, let us take ZD1, ZD2, there may exist only one topology corresponding to it. Meaning is that two distinct metric may induce same topology. And finally what we have seen, that if we are taking a set X with a topology tau, and in discrete topology tau is an indiscrete topology, then corresponding to this topology there doesn't exist any metric on X. What we can conclude from here, that if we are defining a function from collection of metric spaces to collection of topological spaces, then this function is neither 1, nor onto. These are the references which we have used and will continuously use throughout the lectures. The book on Introduction to Topology, Pure and Applied by Adams and Ranjosa. The book on Topology by Monkers and the book on general topology by Billard. That's all from this lecture. Thank you.